Okay, guys, good morning. Top of the hour. Any questions about lab this week? Hydration of norbornene. So we're hydrating an alkene in lab. Your recrystallization worksheet due in lab. Any questions about lab this week? Okay, let's look at carbocation rearrangements. We saw this reaction at where we left off at. Major product is actually this guy over here. This rearrangement, sometimes called a skeletal rearrangement, involved a 1,2 hydride shift. Yeah? Any questions about that reaction? Carbocations are prone to rearranging. You'll see lots of carbocation rearrangements. Another way they can rearrange is an alkyl shift. Let's look at the reaction below. Down here we have an alkene and we have aqueous acid. What are we doing to the alkene? What does aqueous acid do to alkene? Not HBr, not HX, but aqueous acid, hydration of an alkene, right? Hydrate this alkene, we might, where are we going to make cation, top or bottom? That's always the first question. The cation on the bottom. That'd be a secondary cation. That'd be better than making primary cation, right? Okay. And then we can envision water attacking the cation. And if it did, we'd have an OH bonded here eventually. But that's actually the minor product in this case. How do we get this major product? How does the oxygen end up bonded over here? Also, if we look at this, this carbon over here has 3 methyls. Carbon has 3 methyls, yet now the carbon only has 2 methyls. Let's see what's going on here. The first step is no different than any other reaction. Alkene attacks H+. And so we're going to attack here. This hinges out and goes attacks. This gives boom, 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 boom. Mu H there, carbocation here. As we wanted, because this is a secondary carbocation. If we put cation there, it would have been primary. Better cation, right? Okay. We can get this product again from the water, because this is H+ in water, right? If water attacked here, and then we lost a proton from the oxygen as a next step, we could get this product. But that's minor. How do we get major product? It looks like we need this cation. If we had this cation, could you get here? Water attacks and then we lose proton, yeah. How do we get that cation though? Can we get that cation from this one? What do we need to do to get that cation? There's no hydrogen next door, but there's alkyl groups. By the way, this looks a little distracting up here. I mean, is it not there? Yeah, it's there too, but I just didn't draw it over there. That's a carbon with a methyl. Oh, that's a carbon with 2 methyls. One of these methyls, that's a carbon here, 2 electrons in the bond. The 2 electrons break free and move over here. And what does this electron movement give? Carbon with 2 methyls, here, that methyl, used to be bonded here, so I'm going to take the 2 electrons and break them free of this carbon and go bond them over there. Not an H, not a hydride shift, it's just a methyl. But that gives that. But where's the cation at? This carbon has 4 bonds. This carbon, how many bonds does this carbon have? Only 3. There's not an H there, because this comes from here. We moved a methyl that's missing a bond. That's a cation now. How many H's on this carbon? Same number as here. And the same number is there. How many there? 1. There's 1 there, that's why it's a positive charge. There's 1 there, that's why that's neutral. But this is the same as that. I mean, it's the exact same. In this case, we went from a secondary cation to what type?
Tertiary.
Tertiary. We went to a better cation. Not from a hydride shift, but what shifted? A methyl. What's more of a general name for a methyl? It's at the top of your page. Alkyl. YL, alkyl, alkyls, methyls, ethyls, propyls, butyls, all those are alkyls. Alkanes that are substituents. An alkyl shift. It's also a 1,2 alkyl shift, but usually just call it an alkyl shift. From here, so how do we get home? Then water, right? These electrons then attack cation. That gives boom, boom. Oxygen now bonded to the carbon. 1 lone pair left, that's a positive charge. And then we have to lose an H. How can we lose an H? There's got to be a minus here. This is very generic. What acid did we use here? What's a typical strong acid that's used for acid catalyzed hydration? We said this before, like H2SO4, right? Okay, this could have been H2SO4. That means you got HSO4 minus remaining. You could use that, or you could just keep it generic. We could use water to take the H. If water took the H, these electrons bond to the H. These electrons move on to oxygen. We make that, and we regenerate what? What do we make right here? H3O plus. Reformed. H3O plus was the catalyst. We did require 1 equivalent of water, though. So this is another example of a carbocation rearrangement giving sort of an unexpected major product. Although we do kind of expect it, because any time a carbocation can rearrange from like a primary or secondary to something better, we typically do anticipate that. So this was a alkyl shift. Carbocations prone to rearranging by hydride shifts and alkyl shifts. Let's do a reaction coordinate diagram of this reaction here. Starting material A, how many intermediates in this reaction? Total intermediates. How many total intermediates in this reaction? 2? I see 3. Why only 2?
No, it's 3.
I see a secondary cation. I see a tertiary cation. That's just a repeat of this, right? And then I see this intermediate that has a oxygen that's protonated. That we then have to, then we get final home. A, B, C, that's C again, D, and then final product is E, reaction coordinate diagram. You got some type of energy, reaction progress. We start out with A, some arbitrary level. Then we go to B. B is a cation. It's charged. It's higher energy. And so we come up to here, maybe B. C. How does C compare to B? Yeah, it's lower energy. It's a better cation. Better typically refers to energy. Tertiary cation is better. It's lower in energy. So C would be something like this. It's still a cation, but it's lower than B. And then where do we get next? D. D is going to be even lower because everything has an octet. Everything has an octet. See here, carbon doesn't have an octet. Even though oxygen is positive, it's got an octet. That's going to make it better. Eh? So basically, we start out with B, and then from there we start going downhill. I wish I'd kind of moved this higher so I'd have more here, but let's say D. And then we get to what's final? E, which is, how does it compare to A? Pull out your calculator and look at bonds broken, bonds formed. What do you think, though? Why lower? I can't hear you. We broke a pi bond and we formed 2 sigma bonds. We formed 2 sigma bonds. Right? We formed a carbon-oxygen bond, and we also formed a CH bond up there. Those are the 2 new bonds, right? Sigma bonds are stronger than pi bonds. Yeah, D is going to be E, A, B, C, D, E. Be down here. So here we go. We go boom, 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 boom. Transition state leading to B, transition state leading to C, transition state leading to D, transition state leading to E. What's the rate determining step? First step, typically forming your initial carbocation is your rate determining step. These reactions don't take much activation energy because they're falling downhill. Going from D to E doesn't require much activation energy. Just a little tiny bit. Doesn't take much energy to fall downhill. On the other hand, it takes a lot of energy going uphill. Questions about this reaction? Ring expansion. Take a look at this reaction. If we take this compound here, it's got an alkene, it's also got a 4-membered ring. A lot of times I'll write the size of the ring in there just for clarification. Do this reaction with HBr, well, somehow we get a 5-membered ring. We have added HBr because if you take the formula of this formula now has HBr added to it. It is an addition reaction. If we just did a plain addition reaction to the alkene, we would expect that product right there. Just a simple addition of HBr to the alkene. Carbocation, right or left? On the left, and then Br minus would add to the cation. That's how we would get this. But how do we get this? Well, first off, we know that it's called a ring expansion. Because the ring has expanded from 4 to 5. Makes sense, right? Called a ring expansion. Now later on, you may see the rings getting smaller. And what might you call that reaction? Yeah, you got it. So what's the mechanism for this? Well, the first step is the same as the first step over there. We got H plus and we got Br minus if we just want to consider that ionic. And the only reactivity you have here is your alkene. Alkanes don't react with H plus. This is your only reactivity. And this reacts, and you got to make one choice. Are you going to make cation on top or bottom? And the answer is bottom. And it will always be such an answer. And this gives nu H there and carbocation here. And we can get that product pretty easily, but this reaction gives this product as the main product. How do we get that one? Well, carbocations are prone to rearrangement. This is a carbocation rearrangement. The bond next door, that's the carbon. This is 2 electrons. The 2 electrons break free of this carbon and move over. Just like in the previous reaction. Let's break them free and move them over. That is, take this and break it free and move it over there. In this case, though, this carbon is part of the ring. But when we move it over, what do we get? I'm going to draw it just like this. The bond used to be there to make the ring. Instead, we moved it over and bonded it there. The 2 electrons, we moved them over and bonded them there. So now it's bonded there. All right? Windshield wiper. Okay? But how many bonds does this carbon now have? Only 3. Because the 4th one was yanked away. So this is now a plus. That's no longer a plus. How many bonds does that carbon have? Well, how many H's are there? Same number as here. How many H's are there? Same number as here. How many H's there? 1 H, 1 H, 1 H. I just am not drawing them in. 4 bonds to that carbon now. Neutral charge. This one's now positive. There you go. That's an alkyl shift. Just like the previous one, except here, when the carbon shifted over, it actually led to the ring now being a 5-membered ring. Do you see it? Now if we redraw this 5-membered ring more like this, it's a 5-membered ring, 2 methyls next door, 2 methyls next door, and one of the carbons with the methyl is a carbocation. So how about if I was to redraw it like that? Same thing, right? 5-membered ring with 2 methyls next door, and one of them is a carbocation. Now, can you get home from there? How do we get final product? This guy is sitting around watching this. Now, bam. What does that give? You're done. Final product. Br makes bond to carbocation. Did you see that coming? All this is a standard old reaction with an alkyl shift. But this alkyl shift actually led to expansion of the ring from a 4 to a 5. Why would it do this? Why did this carbocation want to rearrange here? This cation secondary, what is it now? Tertiary. There's another reason why we want to do this though. Your job is to give two arguments, not just one. What's your second argument?
Is it Markov-Nikov's rule?
Do what?
Is it Markov-Nikov's rule?
Carbocation. Talking about that Russian chemist
Yeah.
who worked with Zaitsev and those guys back in like 1860s, 70s. That one. Well, Markov-Nikov rule is basically up here. Cation is going to be here.
I just didn't know if that was why it moved.
When we say cation here, there, cation here, that's basically Markov-Nikov rule. But I didn't tell you that because I want you to know that. You can call it Markov-Nikov rule, but who cares? Cation here, that's where we really want to care about. Now, this is more than Markov-Nikov rule. This is what's your argument here? I went to tertiary, but what else would it also do that's better? Yeah, 5-member rings better than 4, right? What size rings are best?
5 and 6.
You said 5 and 6? Did we say that? Yes. 3 and 4-member rings have ring strain. So not only did it go to a better cation, it's less ring strain. This is more stable for 2 reasons. So we came downhill. And then finally, okay, mechanism, yeah? When you first saw it, did it look like, how did this happen? Right here. The shift. But you got to sit down and you got to see this because you're never going to be able to do it if you don't practice it and really see what's going on. Because for some reason, this moving over, here, pull my finger. Most of you just can't see that. And then draw the result because most of you will want to put cation here for some reason, even though there's now 5 bonds there. So you got many things wrong. You got to keep track of H's. How many H's on that carbon right there? Well, there's 0. There's 0. Unless we move one there, there's always 0. There's no H there. There's no H here. There's still no H there. You got to keep track of things. It comes from practicing and making mistakes. The more mistakes you can make, the better you will be. Everybody agree? You start making many mistakes. One below, 7-membered ring, you do this reaction, you get a 6-membered ring. There's your ring contraction. Try that one on your own. But we're hydrating here because we're using this aqueous acid. We're not using HX. Let's look at this reaction. Thus far, all of our reactions have been the alkene attacks H+. That's been the first step. Alkene attacks H+. Can an alkene attack some other plus? It doesn't have to be H+. What about a C+, which we call a carbocation? Can an alkene attack a C+? Let's look at this reaction. You take this is called a diene. It's got 2 alkenes. Diene. What do you want to call a compound with 3 alkenes? Triene, yeah. Tetraene, etc. This diene, you react with HI, this is known to be the major product. It's a cyclohexane. 1,1-dimethyl 3-iodo cyclohexane. Where you put the iodo first, like 3-iodo 1,1-dimethyl cyclohexane. How do you get this product? Well, the first step is, all we have is H+. I mean, just like before, we can call it ionic. You have two alkenes. Which alkene is going to react? Which one would you say is going to react? Well, really what we can do is, before we say top or bottom, we have two choices. Decide where you want to put cation. Well, here you got four choices. Do you want to put cation here, 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 or here? What's the best place to put cation out of these four alkene carbons? 1, 2, 3, or 4?
2.
Yeah. Cation here would be best. It would be lowest in energy. And thus the transition state leading to cation here would probably be lowest in energy. How can we get cation here? Well, first off, this alkene reacting and not that one. But the H plus being attacked like this. These electrons, here, pull my finger. All right? Pull them away from this carbon and go bond up there, leaving the cation here. Pull them away from that carbon. Now this carbon is bonded up there, and we get that carbon is bonded to H. This one is left without a bond. It's the cation. Boom, boom, boom. 1, 2, 3, 4, 5, 6, 7. Oh. 1, 2, 3, 4, 5, 6. Okay. That's it. Gotta be careful. A lot of times you guys lose track of how many carbons you got, etc. So we make tertiary cation. Hopefully we're rewarded and we get to where we want to go. I minus could attack here. Certainly. And that would give us a addition of HI across this double bond, but that's not the product shown. Our mission is to give a mechanism for that product. Instead of I minus attacking here, what else could attack here? We've got another alkene. Have you ever seen alkenes attack positive, like cations? Yes, the alkene just attacked a cation. But does it have to only be H cation? Can it be maybe C cation? Yeah? You got a C cation. Could this attack here? Yes, and that's what happens next. Let me redraw this so we can kind of get it closer. This has free bond rotation, right? These are all sigma bonds, free rotation. Right? It's over here. How's it going to bond? Well, about right there. Let's redraw this. How about if I redraw it like this? Boom, 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 boom. Carbon with 2 methyls. What's a carbon with 2 methyls? See, that looks funny. The H hanging off of it. Forget about the H hanging off it. Carbon with 2 methyls. Yeah, that carbon has 3 H's. I just have one drawn in. The carbocation has 2 methyls. Yeah, carbocation with 2 methyls. Then it's 1, 2, 3, and then the alkene. 1, 2, 3, and then the alkene. This is the same molecule, just rotated around some. Now right here, these pi electrons, by the way, if this alkene reacts, where do we want to leave cation? Right or left?
Right.
On the right. We're set up to do that. Here we go. Pi bond. Somebody pull my finger. Pull them over here, and these electrons go by with the cation. Right? Here we go. Boom. There's your mechanism arrow. What does that give? This bond was just made. This carbon has 2 methyls. See, those electrons used to be over here. They swing over there and became a sigma bond. All right, my bonds usually don't connect. But there's got to be a cation somewhere. Where's the cation? Cation's here. Because that carbon lost electrons. This one's bonded. That one lost electrons. This carbon only has 3 bonds. It's a cation. And there you go. This is a pi bond attacking a positive. But this positive is a carbocation. How do we get home? I minus, where was it at? Somewhere over here, wasn't it?
Right there. Right here on the top.
Bam. And what does that give? It actually gives that. It's just turned. It's a cyclohexane carbon with 2 methyls. And at the 3 away, there's an iota. There it is. Finish up by the iodide acting as a nucleophile and attacking the carbocation to make that sigma bond. So in this reaction, after our initial alkene attacking the H+, how do you describe this? It's an internal reaction. Intramolecular. Intramolecular, the pi bond attacking the carbocation. So we've seen alkenes attack H+, but now we've seen alkenes attack C+. And in this example, it was internal. Intramolecular. And so now we can understand how we can go from that molecule to this one. And largely what we're looking at here is mechanism. Being able to show all your bond formation using mechanism arrows. And arrows show movement of electrons. 2 pi electrons break away and go make a bond to the carbocation. The lone pair electrons make a bond to the carbocation. Every time you move an arrow, you begin by saying what? These electrons. These electrons in the pi bond break away from this carbon and go make bond to H. These electrons in the pi bond. These electrons, this lone pair of electrons. Every arrow begins with these electrons. Down below, polymerization. The other important thing to see here is consistency. Every reaction we're doing has themes in it, but it's all consistent. Themes that will be used as we move forward to create a cohesive story. Not just 10 individualized, memorized things that have no meaning, but if we're building a story here of how to do reactions. Different types of reactions. But each type is not something brand new, it's just sort of fits the trend. Let's look at polymerization. If you take this alkene, pretty darn simple. How we do it in nomenclature? What's the name of this alkene? It's just propene. Nothing else needed. You could call it 1-propene, but there ain't no such thing as 2-propene, so it's really not needed. It's not stereogenic. There's no cis or trans. Propene. If you take propene, treat it with an H+ catalyst, you can get a polymer. By the way, propene actually goes by a slang name. A lot of compounds, when they're out on the street, go by slang names. Propene goes by the slang name propylene. There's a ly added in there. Propylene. Sounds better. What's up, propylene? Propylene. Okay. If you polymerize propylene, what do you get? That's right. Polypropylene. This could be polypropylene, or it may be polyethylene. Usually PPE, polypropylene, yeah, polymer, plastic. Polypropylene tends to be a thin plastic. Or if you want something thicker, using some other type of polymer. This is a structure of polypropylene. Need to look at doing that. Let's look at how we might get catalyst or polymer here. Okay, first step. All we know is alkene's going to attack H+. And we know where we're going to leave cation. Yeah, it's called Markovnikov's rule, I think. I don't know what Markovnikov is, but I heard it's some rule that helps students. It helps you memorize and then not be able to think. That's what I think it helps you do. So that's why I don't ever talk about it. We have, what reactivity do we have? We have pi bond H+. And every reaction we've done has involved that, because that's all we've done this far. Where are we going to leave cation? Left or right? There you go. That's all we know this far. This attacks here. And what do we get? Boom, boom. This carbon now bonded to H because the electrons broke away from this one and bonded to the H, leaving this one as a cation. Secondary cation, not primary. That's Markovnikov's rule. But they say it backwards. Because they don't want you to understand mechanism. They just want you to, I don't know what they want you to do. Okay, cation. Well, what's the minus? Did we use HBr? If we did, Br could attack here and we certainly wouldn't get that product. If we had just used HBr, we might get this product with a new H here. But that's not a polymer. That's just a simple addition of HBr. This is a certain catalyst that does not have an anion. We're not going to have an anion here. What can attack the cation? Well, polymer is where you get just repeating of these. Many of these repeating by reacting. Another one of these can react here. Can an alkene attack a carbocation? We just did it above. But in the above example, it was intramolecular, internal. Could it also be intermolecular? That is two different molecules? Sure, and that's what this example is showing. What about this one? Another one of these attacking this one. Yes. Okay, here's our reacting alkene. Where are we going to leave cation when this reacts? Top or bottom? Bottom. So this is going to pull away from bottom and go attack here. Well, what does that give? Here's where you have to sit down and make some errors and then eventually get it right. Keep track of this. I'm going to sort of start here. Boom, boom. Cation here. This carbon wouldn't attack the carbocation. This is this carbon. This carbon has two methyls. Okay? Which bond did we just make? I like to highlight that right there. That's the bond we just made. This used to be carbocation. These electrons swung up and bonded to it. The carbocation is bonded to two methyls. The carbocation is bonded to two methyls. Yes, I drew in this H. Let's draw it in again because we can keep track of that. Because this is their initial hydrogen. Let's keep track of that. The very initial hydrogen. Do you want to number these? 1, 2, 3. 2 was the carbocation. 4, 5, and 6. What's bonding to each other? 4 is bonding to 2. 1, 2, 3. 4, 5, 6. 4 bonded to 2. That's what that arrow is showing right there. But see, some of you guys will think it looks like 5 is bonded to 2. No, that's because my arrow means I'm pulling these electrons away from 5. They're staying connected to 4. They're pulling away from 5. They're still connected to 4. 4 is bonding to 2, leaving 5 without a bond. We made a bond between 4 and a 2. I highlighted that. Okay. What can attack this? How about another alkene? We call this 7, 8, and 9. Which carbon is going to bond to 5? 7. Where do you want to leave cation at? On 7 or 8? On 8. That's why 7 is the one that's going to bond to 5. Because if 8 bonded to 5, you'd be leaving cation on 7. Cation goes on 8. If you pull away from 8, this hinges up. 7 goes and bonds to 5. What does this give? The original boom, 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 boom. 1, 2, 3, 4, 5, 6. Now we have 7 bonded to 5. 8, 9. 7, 8, 9. The pi bond used to be between 7 and 8. But the pi bond broke away from 8 when it made a bond to 5. We just made this bond between 7 and 5, leaving 8 as what? Carbocation. What can attack 8? Another one of these. Stop me when you want. How many times? This happens a billion times, and you end up with a huge, long... What? How do we draw this before it gets too complicated? By the way, this reaction was started by this attacking what? A cation. That's why it's called cationic polymerization, because it was started by attacking a cation. If it attacked an anion, it would be called a anionic polymerization. Okay? This is the initial H. The very end is often up for debate. That's advanced polymer considerations. Eventually, this can end some way after it gets hugely long. The important thing in this point is how do we show this? Let's look for repeating units. The H doesn't repeat. The initial H was only there at the beginning. All the other H's were there already. Look at this. After the initial H, CH2, carbon methyl. CH2, carbon methyl. CH2, carbon methyl. If you look at it, it's like that repeating. And we can draw that here. After the initial H, CH2, carbon methyl. CH2, carbon methyl. CH2, carbon methyl. See, it's repeating. But this right here is what's repeating in parentheses here. We show the repeating unit in parentheses, and then we give it an N. N is some huge number of repeating units, like 100 gazillion. And this is how you would show the polymer. Just what's in parentheses, that's all that's needed. I just showed a little bit more. So being able to put this together mechanistically and then showing the repeating unit in this style and knowing what is the repeating unit. The repeating unit is your monomer, really. It's 3 carbons. So the repeating unit is going to be 3 carbons. But it's CH2C methyl. Questions about polymerization?
Are you counting, when you say CH2, are you not counting the hydrogen, the cation, right? When you say CH2, you're not gonna count the one. Because the end one is a methyl, right?
I'm sorry, I can only hear every other
Sorry.
word.
So the original H that you, the cation that you added on ended up making that carbon a methyl, right? Because it already had two hydrogens on it, right? That one, yes, but you said CH2, a carbon and a methyl. So are you're just not counting that hydrogen that we added? Is that what you keep saying, CH2?
Well, if we called that a methyl, there would be no repeating unit because that's not a methyl.
Yeah, so
That's
that's
not
why
enough.
I would have put the parentheses around the other half, and I just want to know why wouldn't we? If that makes sense.
Around what other half?
Like I would have started it in the middle. It's like on the next repeating unit, since that's like the true repeating unit. That makes sense?
Yeah, but any one that I circled over there or put in parentheses over there would be the same as what I put in parentheses here. Would it not?
Thank you.
So it doesn't matter. I mean, I could have encircled this right here and told you the repeating unit was CH2C methyl. But that's what I told you over here, CH2C methyl.
Yeah, so you're just not counting that last one. Okay, I got you.
The repeating unit is CH2C methyl. CH2C methyl. Okay, there's a little bit of homework question there. THC. Let's see how you're doing on that one. Mother Nature's a wild and crazy chemist. How do we go from cannabidiol to tetrahydrocannabidol, which is the major component of marijuana? But the marijuana plant makes this molecule. We call it a natural product. But it's standard chemistry, the same type of chemistry we're looking at. They show a mechanism for that reaction. Anti-transition. Okay, let's see where we're at on the green sheet. We did all these reactions up here. All these reactions involve reaction with an H+. These all involve a carbocation intermediate. Didn't every reaction we did have a carbocation? Okay, that's up here. Including making ethers. We'll now move down to these reactions. These reactions will involve other electrophiles other than H+. Actually, none of them will involve reacting with H+. H+ is all above. These reactions will not involve a carbocation intermediate. They will not. They do not involve a carbocation intermediate. And are thus not prone to rearrangements. That's a good thing. But you only get rearrangements when you have a carbocation. If these don't have carbocation, you thus don't get rearrangements. And we've covered all of A on the outline. We're ready to start with B. Need to be doing some reading. Because we'll pick it up a notch. And if you're not following what we're doing thus far, then you're going to start getting more and more behind. Okay? Please be doing some reading about the upcoming topics, etc., etc. And have a good day, guys.